All right, we're back with the second half of the chapter 20.1 through 5 videos. This time we're going to talk a little bit more about applications of our spontaneous reactions as far as oxidation reduction reactions are concerned. So just like we learned in our previous section or our previous chapter, spontaneous reactions occur and all types of spontaneous reactions occur. So we're going to take this and we're going to use one of the applications of those spontaneous reactions. In this particular reaction, electrons are going to be transferred, and when that happens, energy is released, and that's a spontaneous redox reaction. And in this case, the other thing that we're going to look at is how to actually calculate the delta G of what we call a voltaic cell. So that's our goal in this particular section. For now, what we're going to do is we're going to look at how we can use energy to actually set up what we call a voltaic cell. And you're going to see some things like solutions and electrodes, solutions and electrodes. Now, normally we would do our own lab with this and create our own voltaic cells. And since we're not in person, it's probably not going to happen. We may do like a mini lab next week, but to finish out this chapter and the end of school is next week. I don't know yet. That being said, we have two parts of a voltaic cell that we have to learn to assign. The first is going to be the anode and the second is going to be the cathode. So the reduction reaction has to occur at what we call the cathode. Cathodes are also positively charged. Anodes are going to be where the oxidation is going to occur, and they're going to be negatively charged. So now if we look at our diagram in front of us, what we're going to see is that the oxidation reaction, where electrons are being lost, remember oil rig, our zinc is going to lose electrons to create the zinc 2 plus and 2 electrons. In our reduction reaction, we're going to see that reduction, where the electrons are gained by the positive species to become neutral, is going to be over here. And so what we're going to see is that anions are going to migrate towards the negative thing, and cations are going to migrate towards the positive thing. This salt bridge is going to actually be there. It's kind of like the completion of the overall reaction. So think of this as like a circuit. And in order for electrons to flow along a circuit, what has to happen is they have to be connected. And so electrons are going to move from the negative side. I'm sorry about the mower. From the negative thing that's charged, so the anode is negatively charged, electrons that are also negatively charged are going to try to get away from the negatively charged thing and move towards a positively charged thing. So our cathode, being positively charged on the right side, is going to have the electrons move toward it. And since that's the case, in order to complete this, we have this salt bridge, which allows for migration of our negative and positive things. So that's just one thing to kind of consider. When we talk about electron flows, just make sure you know that the idea is that electrons will flow from the anode to the cathode. That's the way that we talk about it. So always anode to cathode when it comes to electrons. If your voltaic cell is set up correctly, electrons will move from anode to cathode. I could say it 100 times and it still would not be enough. So that being said, moving on to how we can use these. So if we talk about the salt bridge in particular, one of the things that we want to make sure is that it always contains a salt solution. So in our case, in this example, we have a salt solution of sodium nitrate. And in that salt solution, since those salts are very good at breaking up and dissociating in solutions, what they do is they break up into cation and anion. Now the cation will move towards the cathode and the anion will move towards the anode. And just doing this helps keep charges in each solution balanced. You have to have balanced charges in order for the electrons to move. And then just understand that there's more than one way to create these things. There's a way that you can just like put something in between two solutions and you can actually create a salt bridge just by creating a semi-permeable barrier of some kind. What we want to just make sure is that any voltaic solution or any voltaic cell that we create has electrons flowing from the anode to the cathode, and has anions transferring from one half to the other and cations transferring the opposite direction. Now, the other thing that we want to talk about is how electrons are taken by the cation. So for instance, if the cations are positively charged, then electrons are going to be attracted to them. So having a positive cation in solution actually attracts the electrons even further to them. Okay. The next thing to talk about is an electromotive force, and this is actually a concept that's used a lot in biology for proton pumps and how ions get pumped from one side of our cells to another. And we think of this like a waterfall, right? So in a waterfall, water only goes one direction, and it can only go one direction, right? Like our water can't go back up the waterfall. That would defy the laws of gravity and physics. So if we think about it from a potential energy standpoint, when we are at the top of the waterfall, our water has a lot of potential energy. At the bottom of the waterfall, however, it's expended a lot of that potential energy into kinetic and now has lower potential energy at the end. The same thing can be said of electrons. Electrons will only spontaneous flow in one direction in a redox reaction, from a higher potential to a lower potential energy. So one of the things we want to learn how to calculate or interpret is the potential energy of any of our redox reactions. And we're going to use this, and we're going to call this potential difference between anode and cathode the electromotive force. So it's just a fancy term for the difference between an anode and cathode and the potential energy difference between the two. We also refer to this as a cell potential, and more often than not, I will say cell potential, and we'll call it E sub cell. Okay, so our reaction is going to have a unit of volts. So you've heard the term volts before. This is just going to be the way that we measure the potential of our cell. 1 volt is equal to 1 joule per coulomb. Don't worry too much about that. Just know that the value is the volt. Our reduction potentials have been measured just like delta H's and delta G's and delta S's. All of these standard reduction potentials have been measured for a lot of reactions. Remember, not a lot of chemistry is brand new. And the brand new chemistry discovery stuff is not the kind of stuff you have to study initially, right? So initially, we're actually going to study reactions that have already been put together. And so, for instance, we know that someone has actually already measured the cell potential of an iron atom with a 3+ charge, gaining a single electron and becoming an iron 2+ charge. In other words, the reduction of iron 3 to iron 2. These are all reduction half reactions. However, you can flip them around to get oxidation half reactions. And we'll talk about some of the ways that we're going to treat this when we do some practice problems with this stuff in the near future. But just know that standard reduction potentials have been measured at 25 degrees Celsius, again, the most common. They've been measured and tabulated. They're in tables. Okay, their values are all compared to a single hydrogen electrode. We call it the standard hydrogen electrode. And because we've compared it to that, we've defined the hydrogen electrode as having a 0 voltage reduction potential. So here you can see on this table that the hydrogen reduction has a 0 potential. So whether you write that forward or backward, you're going to get a 0 potential. And we compare everything else to that. So all of those other reactions have been hooked up to the hydrogen electrode, and they've been measured as a standard against that potential. From there, we can talk about how to actually calculate the standard reduction potential of a cell, and that's E naught cell. We're going to do that by taking whatever the reduction potential is at the cathode minus the reduction potential at the anode. Okay, so again, these are going to be values we find from a table. Our big thing is going to be making sure we find the correct reduction potential for the cathode and the correct reduction potential for the anode. All right, so here we have a cell that has the zinc and the hydrogen electrode, and for one side of the reaction, we're told that the oxidation in the cell was negative 0.76 volts, and that for the reduction, it's positive 0.34 volts. In order to calculate the potential of the cell, then we're going to take the cathode value, which was the 0.34, and we're going to subtract the anode value, which is a negative 0.76, and we're going to get a positive 1.10 volts. So that's just how we do the potential of the cell. Next thing to understand is the how oxidizing and reducing agents work. Remember that this term oxidizing agent and reducing agent comes from the beginning of this chapter, so go back and review what it means. The strongest oxidizers are going to be the ones that have the most positive reduction potential, so they're going to be at the top of the chart, and the strongest reducers are going to have the most negative reduction potential, so those are going to be at the bottom of your chart. The greater difference between the two, the greater the voltage is going to end up of being for the cell. So one of the things I do want to point out here, and it's something that for some reason, I don't know why the wrong diagram is in our previous slide, but that cell potential that we calculated was for a copper cathode and a zinc electrode. I'm sorry, a zinc anode. Now, back here, it shows a hydrogen electrode. We know that's wrong because the hydrogen electrode would have a reduction potential of 0. So just keep in mind what they're actually showing you. What they should have shown you is this particular cell. We calculated the cell potential of this particular voltaic cell, and that is different than what is in your book. So just kind of pay attention to what's labeled as the anode and the cathode. So for us, the actual anode was the zinc anode that we originally thought, but the cathode should have been the copper, not that hydrogen. So just keep that in mind. Then we calculated the potential by taking the cathode minus the anode potential and getting a positive 1.10 volts. All right, from there, we just want to revisit Gibbs free energy. And this is the first way that we can calculate Gibbs free energy using cell potentials. So we can use a redox reaction to figure out what the delta G is for the reaction by knowing a few things. N, which is going to be the number of moles of electrons. So the number of moles of electrons transferred. So if it's 1 electron or 2 electrons or 3 electrons, etc., the N is going to be a whole number integer. F is a Faraday constant. So Faraday constant meaning a constant value. And then E is going to be the cell potential. So under standard conditions, the standard delta G will be equal to negative N times the Faraday constant times the cell potential, the standard cell potential of the overall redox reaction. All right, next week we're actually going to start covering what we call non-standard conditions, so the Nernst equation. But this is the end of our section 5, so I'm going to stop us there. And remember, you have the practice problems video to look forward to in the near future.